Welcome back, guys. This is going to be the second part to the 8.7 instructional videos. And in this video, we're going to kick things off by actually going back to our definition of exponential functions. Here you can see on the screen the general form for an exponential function, y equals a times b to the x, where a is your starting amount or your initial value, b is your rate of change, and x is the number of times your rate of change occurs. Okay, and any exponential function will be in some form or another of this. Okay, y equals a times b to the x. But I think in the part one video, I did not touch on some of the base requirements, so I wanted to make sure that these were understood. So what are some requirements that we have for a function to be considered or an equation to be considered an exponential function or an exponential equation? Well, obviously they have to be in the form y equals a times b to the x, but in particular, a cannot be zero. Okay? A cannot be zero. And why is this the case? Well, if theoretically you had an exponential function like this, okay, it would not be an exponential function, because what would happen is no matter what x turned out to be, no matter how many times your rate of change occurred, whatever number it may be, you're going to have 2 to that power and you're going to get some number. When we multiply that value, 2 to the whatever exponent, by 0, you will just end up with 0, because anything times 0 is 0. Y equals 0 is a horizontal line. It is not an exponential function. It does not produce that curve we are looking for. So a cannot be 0. So even if for some reason you would have something that looks like an exponential function, if that a value, that initial amount, is 0, it will not be considered an exponential function. Okay? Our second requirement, b must be greater than 0 and b cannot equal 1. B must be greater than 0 and b cannot equal 1. You will see algebraic equations and expressions where b is in fact a negative number. It is not bigger than 0. It is not bigger than 0. But they are not considered exponential functions, and they are not considered exponential equations. Their graphs will not produce the curve that we have looked at in 8.7 part 1 when we graphed it. Okay, so b cannot be negative. We also cannot have a b value of 1. This gets at the idea of 1 to any power is just going to be 1. And so what you're essentially going to have is your initial amount times 1. So again, you're just going to get y equals some number, which again is a line, not an exponential function. Okay, it would be considered a linear equation or function. Okay, and again, you cannot have b be 0. If b was 0, you would have 0 to the something power, which is either going to be 0 or it will be undefined. Again, we've already kind of touched on that with a not being 0. There aren't any real restrictions for x. X can be any real number. You don't quite know yet in algebra what imaginary numbers are, so that should not trouble you. So x can pretty much just be any number. Okay? So again, I think these requirements are important for recognizing exponential functions. So to make sure you're getting it, give yourself a little quiz here. I'm going to put up 3 functions, or rather 3 equations. You tell me if they are exponential or not. Actually, we'll do 4. Okay, so give yourself a little quiz. Just mentally make a note. Maybe you jot it down in your notes next to the requirements, these examples. Which of these are considered exponential functions? Okay? And again, I think these requirements are really good to go through because All of these look like exponential functions. They have the shape of them, but some of them are disguising themselves and looking like exponential functions when they really are not. So let's take a closer look at the first one. Is this an exponential function? It is. Now, it might have concerned you. You might go, wait a minute, Mr. Carter. I don't see an a value. Does that mean the a value is 0? Well, no, because again, if the a value was 0, you would just end up with y equals 0. So what is the a value when we don't see a number written there? Well, the a value would be 1. Okay, the a value would be 1. So maybe I draw a little 1 in there. Okay. Again, this meets your requirements. Your b value is greater than 0 and is not 1. Again, x could be any real number, but obviously here we don't have any x values that we are plugging in. Y equals x to the fourth is not an exponential function. Why not? Well, your b value, your x, is in the position of your b value, and we have a constant where the x is. Okay, y equals x to the fourth is not an exponential function because your x needs to be in the exponent. Okay, y equals negative 2 times 1/2 to the x. This will be an exponential function. Again, your a value is not 0. Your b value is bigger than 1, but it is not equal to 1. However, your last example here is not considered an exponential function. Why? Because you have a negative value for your b. And again, while there are algebraic expressions, equations out there that do have this form, they are not considered exponential functions. So hopefully those requirements seem clear. Hopefully you have a better understanding of what is and is not an exponential function, in addition to understanding from the previous video what the general shape of exponential functions look like. So let's move on from there and let's look at one more graphing example. I believe we covered one graphing example in the previous video. Let's cover another example here just to make sure we're shored up on it. Again, remember to graph exponential functions. Let's say we're graphing y equals 2 times 1/2 to the x. Okay, y equals 2 to the 1/2 x. Yesterday, I think we graphed y equals 3 times 2 to the x, which we'll address here in a little bit. So again, how are we going to graph these? What we're going to do is we're going to identify some x values. For your benefit, I would say always use the following 5. 5 is going to give us a good picture of what the curve looks like. Okay, it's going to give us a good picture of what the curve looks like, but it isn't going to overwhelm us with millions of x values to plug in. It's also going to have some relatively easy numbers. We're not going to be dealing with any high values, which is important because with exponential functions, x is your exponent. And you're going to see what things look like on both sides of the axes, the y-axes. So we identify x values. Then what we're going to do is we're going to plug all of these x values into our function here in black, and we're going to find the appropriate y values. So 2 times 1/2 to the negative second. And this is where exponent rules really come into play. We saw in 8.5 that if we have a quotient in parentheses to a negative exponent, we can flip that quotient and we can rewrite our negative exponent as positive. I know 2 over 1 can be simplified to 2. So I get 2 squared, which is 4. My y value when x is negative 2 is 8. Follow the same logic for 2 times 1/2 to the negative first power. And we're going to get 2 times 2 because 2 to the first power is 2. And we end up with 4. Once we get out of the negative exponents, things become a little bit simpler. Anything to the 0 power is just 1. So we end up with 2. 2 times 1/2 is 1. 1/2 comes from 1/2 to the first power. And finally, we'll make a little bit more space up here. Again, when we have a quotient in parentheses, we can distribute the exponent. So I get 1 squared over 2 squared. That goes back to our quotient to a power idea from 8.5. So I get 2 times 1/4, which comes out to be 0.5, or 1/2. So I have my x values. I found the matching y values, again, using my exponent rules from 8.1 through 8.5. And now what I'm going to do is I'm going to plot them on the graph. And connect them with a line here. And again, I think we discussed this in the previous video, but it's worth mentioning. This curve will curve off and will never hit the x-axis. Okay, I think we showed some physical examples of why this will not hit the x-axis, because you essentially get a number like 2, your a value, being divided by a massive or multiplied by a fraction with a massive denominator. In other words, 2 is going to be divided by a massive number. I think we showed that in the previous video. But if you want to think about it a little bit more abstractly, what has to happen in order to hit the x-axis, to intersect it? Well, whenever you hit the x-axis, and we talked about this when we talked about x and y intercepts, when you hit the x-axis, your y value has to be 0. Because x is in your exponent in these algebraic or your exponential functions, because x is in your exponent, there is no value of x that we can plug in that will make y 0. It doesn't matter if x is a negative, a positive, or 0, as we can see in the table. There is no value that we can plug in for x that will give us a y value of 0, which is why our curve approaches the x-axis, but it never comes into contact with it. Now let me outline our curve from yesterday. It looks something like this. And hopefully what you see here, our curves are kind of opposites, okay? They have the same general pattern, but one starts off high and works its way toward the x-axis. The other one starts its way at the x-axis and works its way up in the air. And this is not just a unique coincidence, but a pattern with the graphs of exponential functions. And really, you could summarize the graphs of all exponential functions in a table. And so when we graph exponential functions, while some may be steeper than others, they all broadly are going to fall into one of these 4 categories. The first category is like the one we graphed yesterday. If, I'll write it in red, it's probably a better, or black is a better choice. If your a value is positive, which my a value here is 3, and your b value is greater than 1, right? Our b values have to be either between 0 and 1 or bigger than 1. If your b value is bigger than 1, then you are going to have an exponential function that starts above the x-axis, approaches it on your negative x values, and as your x values increase, it moves up toward the sky. It shoots up toward infinity and increases at a drastic rate. That's similar. Our graph from yesterday, 3 times 2 to the x, would fall in that category. Our graph from today, though, 2 times 1/2 to the x, would fall in the category of still having a positive a value, but the b value is less than 1. And again, probably a little bit better to write it like this, right? We know our b value can never be 0 or less than 0, but your b value is a fraction in between 0 and 1. In this case, our b value is 1/2. And when that b value gets below 1, what happens is your graph almost flips across the y-axis. And now your high point is going to occur when x is negative, and as x increases and turns positive, your graph is now going to approach that x-axis. Okay, so they kind of flip pictures. Okay, they kind of flip across the y-axis, and that's the effect of going from a b value bigger than 1 to a b value that's in between 0 and 1. Now, what we haven't explored is what happens when your a value is negative. And while your b value changing from being greater than 1 to in between 0 and 1 flips your exponential functions across the y-axis, your a value becoming negative is going to flip your exponential function graphs across the x-axis. So an example of this would be maybe negative 3 times 2 to the x. And again, we still, because our b value is bigger than 1, have that characteristic of when x is negative, we are approaching the x-axis, but as x grows and becomes positive, we kind of shoot downwards in this case. The y values take off and increase dramatically. Okay, but instead of shooting upward, we are going downward, and that has to do with your a value being negative. If your a value is negative and your b value is between 1 and 0, then what you're going to have is that opposite situation, similar to that of when your a value is positive and your b value is between 1 and 0. You're going to have, in your negative x values, you're going to be shooting off toward low y values. But as x becomes positive, that's when we notice our graphs start to approach the x-axis. Okay? So hopefully this chart really just gives you a good idea of the general different ways that exponential graphs can look. And hopefully you can use it as a key to help yourself that when you're graphing exponential functions, you can go, hey, what category, which of these 4 categories does my exponential function fall in? And does my graph look roughly like that? Guys, I appreciate you watching. This will include 8.7 part 2. Have a good day.